Logistic regression is used to test the relationship between two or more variables when the variables are binary, meaning they're coded as yes, no, true or false. This is in comparison to linear regression, where you can actually plot the variables on a y and x axis. In logistic regression, you only have two responses, yes and no. These variables are converted into zeros and ones because that's how the math works. It's actually calculating the log function from 0 to 1, hence the name logistic regression. So let's see how that works. I have a data set here of chronic health conditions, and I want to test the relationship between atrial fibrillation and hypertension using logistic regression. First, let's look and see how these variables are coded. So we have atrial fibrillation here as a variable, and importantly, if I go to the values column, you'll notice that I have these coded as no for atrial fibrillation as a 0, and yes for atrial fibrillation as a 1. And the same is true for my hypertension variable. So these are binary responses. Also note that both variables are coded as a nominal variable here. They're not scale variables in this analysis. If I was doing linear regression, I could be using scale variables, but that's not the case in this analysis. So to run the analysis, I'm going to go to Analyze, Regression, Binary Logistic, and I'm going to put atrial fibrillation in as my dependent variable. And hypertension as my independent variable. A couple of options here. I don't have to list hypertension as a categorical variable because there's only two responses, yes, no, 0 and 1. But if this was truly say an ordinal variable or multiple responses, then I would have to identify this as a categorical variable. Under the options, keeping this simple, you're probably always going to want to select the Hosmer or Lima-Shaw goodness of fit. And we only have one independent variable, so we're just going to use the enter method here because it's going to just push one variable into the model. What you'll see here is first case processing summary, just looking at the total number of variables. You can see I have a very large data set here. My dependent variables coded as 0 and 1. The logistic regression in SPSS always starts with the block 0, which is really the model when there's no variable. You'll notice here hypertension is not in the equation in this model. So when you get to block 1, that's where you're going to see, first of all, your model summary. And what you have here are two what are called pseudo R-squares, the Cox and Snell, and the Nagelkerke. These are analogous, but not exactly the same as an R-square used in linear regression. And the difference between these two numbers, the Cox and Snell, is on a scale of, I believe, 0 to 0.7, whereas the Nagelkerke is on a typical 0 to 1. So the Nagelkerke is a little bit more intuitive if you're trying to compare it to a general R-square with the variance. But keep in mind, these are not exactly the same. The Hosmer-Lima-Shaw test, a very sensitive test, and what you're looking for is a sig of greater than 0.05. Next, you have a classification table, and this is looking at the predictive value of this model. And what you notice here is the predictive, it's pretty good at predicting when you don't have atrial fibrillation. it's not as good at predicting when you do have atrial fibrillation. So the overall percentage is high, but keep in mind there's quite a bit of a difference here. And then finally, the variables in the equation. What you're looking for is, first of all, of course you have your beta weight and your standard error. The Wald statistic is the test statistic used in logistic regression. So similar to an F value in ANOVA or a T value in a t-test, you have the Wald statistic and you get a significance level. Sig here is quite a bit less than 0.05, and the AXB here is the odds ratio. So the odds ratio here is 19.3. Now I'd like to show you how to add more variables to the equation. So again, you can go back to Analyze, Binary Logistic. We already have our two variables in the equation. Both of these variables are binary variables, but you can add scale variables as an independent variable. So atrial fibrillation is a much more prevalent in older people. So I'm going to put age in here as well. So now I have two variables in my equation. And we're still going to use the enter method. There are other options. There are forward and backward, conditional, and likelihood of risk methods. But for this simple linear regression, we're just going to keep it with the enter method. And again, I have my classification, my block 0. We're just going to jump down to block 1. You'll notice we have a much stronger Nagelkirche score, 0.273. The Hosmer-Limachow is now less than 0.05, so that is something to consider. The classification table is slightly better with age. And then you'll notice here we have the two variables in the equation. We have hypertension. The odds ratio actually dropped. Obviously there's probably a relationship here between hypertension and age that would need to be accounted for. But that's how to do a logistic regression using one dependent binary variable, one independent variable that's binary, and one independent variable that is a scale variable.